All right, thanks everybody for giving me the opportunity to present today on work that we've been doing using DualSPhysics to simulate surf zone hydrodynamic processes across a fringing reef that are driven by irregular waves. And so this is work with a number of collaborators listed here. So the work that I'm going to present here was initially motivated by prior work that we did looking at surf zone hydrodynamics driven by regular waves using DualSPhysics that have been published in this paper a couple of years ago in Ocean Modeling. And so the focus of this paper was for this very simple regular wave forcing to assess the ability of DualSPhysics to simulate some of the detailed hydrodynamic processes of wave transformation, mean water levels, so setup variability, also undertow profiles, as you can see in a number of these figures here, really for benchmark cases. So we simulated a linearly sloping plain beach and also a fringing reef and compared this to experimental measurements that you can see here. So what I'm going to be focusing on here is numerical simulations of a regular wave transformation across a fringing reef. And so this is based around some physical modeling studies that we did of a reef 1/36 scaled fringing reef that was constructed in a 55-meter wave flume. This is a really rich experimental data set where we had 20 wave gauges across the reef, as you can see here, 6 velocimeters, georeferenced imagery, as you can see in the video, and also wave run-up gauge at the beach behind that. And so this has really enabled, as you'll see, doing a really detailed investigation of a regular wave transformation. And importantly, the evolution and generation of very low frequency infragravity wave motions that are generated by the sea swell waves, and also things like wave setup and run-up dynamics with these detailed measurements. And so when attempting to simulate this problem, I just want to really emphasize that there's a number of quite substantial challenges with this setup. So the first being that we have a challenging bathymetry profile. So this is showing the correct aspect ratio where we have waves that break on a reef slope. Then they reform and they propagate largely without much dissipation across this very wide and shallow reef flat. We also have a large model domain, so we're interested in simulating some of the shallow water hydrodynamic processes in this region, but offshore we have a really large volume of water in this 55-meter wave flume. To simulate the critical infragravity wave dynamics, we also need to run very long simulations, so really hundreds to almost 1,000 individual wave periods. And as I'm going to talk about, what's really enabled these simulations to occur and really get robust results is really some of these new features that are embedded in version 5 of DualSPhysics. And so in terms of the numerical setup, we used settings that were in many ways similar to the previous paper that I mentioned, but with some key differences. So we used the new modified dynamic boundary condition in version 5 of DualSPhysics, the new density diffusion term, also used a laminar plus subparticle scale closure viscosity treatment based on the Smagorinsky approach with a kinematic viscosity that's physically based, so it's 10 to the minus 6 meters squared per second. We used model coupling with swash using inlet-outlet boundary conditions. And the final simulations use an inner particle spacing of 3 millimeters and were run for 960 seconds. So just to give you an example of the simulations, what's being shown here is a zoomed in region of the reef crest where we can see these incident waves, regular waves that shoal and break quite violently on the reef crest, generate bores that reform and propagate across the reef flat, which you can't see. So one of the advantages that we had with this experimental data is this detailed georeferenced imagery, which we can show just one example of one breaking wave. What's plotted in red here are the isosurfaces output from DualSPhysics. And we can see the model really captures a lot of the features that we see in reality. So we can see the steepening of the reef as it approaches the crest, the overturning of the plunging wave, a splash up event, and then a bore that then propagates across the reef. So quite good agreement we find with this approach. So here I really wanted to show some of the comparison with the model prediction with the observations of wave transformation across the reef. So what we can see here is measurements at a number of gauge and the evolution of the waves and the wave shape across the reef, going from offshore here, where we can see that we have these large waves, to skewed and asymmetric waves, to these bores that develop and propagate across the reef. And we can see there's quite remarkable agreement in terms of reproducing this full range of wave shape evolution across the reef. Similarly, we can compile all this information and predict bulk parameters. One of the things we're really focusing on this work is looking at the different wave motions in different frequency bands. So we have our incident kind of sea swell waves, which are dissipated and reproduced by the model. But we also have a lot of energy in these infragravity wave frequencies, which we're separating into a high infragravity wave band. In field scales, this would be 25 to 100 seconds, and low frequency motions, which are really slowly varying, greater than 100 seconds. Because of the increase in these low frequency IG waves across the reef, we get an increase in the spectral period that's well reproduced by the model. Likewise, an increase in the spectral bandwidth. And finally, we can see that the model accurately reproduces the setup profile across the reef. So this shift in the wave spectrum from energy concentrated in sea swell frequencies to low frequency infragravity waves is really illustrated well by these comparisons of wave spectra across the reef, where initially offshore of the reef crest, we can see we get this dominance of energy in the sea swell bands, which is basically to the right of this vertical dashed line. But as we move towards shore, we can see this growth of low frequency wave energy to the point where we get to the shoreline. We can see a really dominant energy concentrated in these very low frequency motions. And we can see the model really accurately reproduces these trends across the reef. So with this experimental data, we have also detailed wave run-up measurements with a wave run-up gauge, which is deployed along the beach slope, which is shown here. And we can compare that with the model predictions to these experimental observations. What's shown here is a comparison of run-up time series. This is just taking a 5-minute segment of the simulations, where we can see very good agreement. Also, really, the dominance of these oscillations are really very low frequency motions that are resolved by the model. And we can see that, and another way to show that is with the wave run-up spectra, where we can see this dominance at the shoreline in terms of wave run-up of these very low frequency motions, which are picked up by the model. So I want to finish by talking a bit about some of the new features of version 5 of DualSPhysics and how they're really central to getting the results that we're achieving. So as I mentioned, we're using this new modified dynamic boundary condition approach and the new density diffusion term. And what's shown on the right, these are part of a number of sensitivity tests that we did, but this is just showing some of those, the effect of those features. So the blue line is the current simulations, what I've been talking about here. We're using the new modified dynamic boundary condition and density diffusion term. As you can see, if we just use the original dynamic boundary condition, the orange line, we get a much greater attenuation of waves across the reef. Setup is okay, but what we find is that as we get across the reef and all the way to the shoreline, that wave run-up is severely underpredicted. Similarly, if we use the original density diffusion term, and this is sort of a known issue, that when you have breaking waves and plunging breaking waves, you can have issues with the mean water level anomalies that are occurring in the surf zone, which we can see here. And so all up, it's really these new features that have been really central to obtaining these accurate results that we're obtaining in this present study. So I finally just want to briefly talk about the important role that viscosity plays in this problem. So as you can see in this simulation where we zoom out and we see the entire reef flat, you can kind of get the sense of how challenging this is, where we have waves that break and then they reform, and then we have waves that are irrotational and don't dissipate much energy as they move across the reef. So how we deal with viscosity is really important if we want to accurately produce, for example, wave run-up at the shoreline. In the present simulations, we use the laminar plus SPS approach using a physically based kinematic viscosity. I should also mention, however, that we did do initial simulations using an artificial viscosity approach, using initially typical values of alpha about 0.01, which proved to be too dissipative. But what we found through this process is we could actually reduce these artificial viscosities down to actually 0. And with this new density diffusion term, also create stable simulations that were comparable actually to this laminar plus SPS approach. So there's clearly more work to be done on what's the optimum way to simulate viscosity in this case, but it's clear that we really need low viscosity and this density diffusion term to create a stable simulations. So to conclude, I just want to briefly summarize some of the main results. So as we've seen with DualSPhysics, and in particular incorporating some of these new features within version 5 of DualSPhysics, we're now able to really accurately simulate the wide range of surf zone hydrodynamic processes that were in this rather complicated case of wave transformation across this reef. With swash coupling and the new inlet-outlet boundary conditions, we're able to greatly increase computational efficiency by really a factor of 7 if we compare that to what would have occurred if we had to simulate the whole flume with DualSPhysics. This then enables longer duration simulations where we can simulate 400, greater than 400 peak wave periods. That also enables us to simulate these very low frequency wave dynamics, including the role that they play in wave run-up. And so just to finish, I want to acknowledge the Australian Research Council for supporting some of this work, and also discussions with Tomo and Jose along the way that have proven really invaluable. All right, thank you.